Hello everyone, my name is Jason Gregerson. Welcome to the next video in your Calculus 2 video series. Today we're going to continue on our discussion about convergence tests. In this video we'll focus on the alternating series test. So what is an alternating series? Well, it's a series where the sign changes with each new term. So in other words, I have positive, negative, so on and so forth. Now it turns out if we have an alternating series, we're going to be able to check two core conditions to directly determine whether the series is convergent. The first criteria says that b sub n plus 1 is less than or equal to b sub n. Well, what does that mean? It means the next term is less than or equal to the previous term. In other words, the terms of the series are non-increasing. It doesn't necessarily mean decreasing, just not increasing, because they actually can be equal. The next criteria is the limit of the b sub n's as n goes to infinity is equal to 0. So now that we've seen the conditions, let's see if we can put this theorem into action. Here we have two series, and all I have to do is verify or show that each of the criteria are met, and then I could say whether the series converges. Alright, so for the first series, if I write this in expanded form, when n equals 1, for instance, I would have positive 1 over 1, or 1. The next term would be negative 1/2, then positive 1/3, minus 1/4, so on and so forth. So let's check my criteria. I have 1/2, which is less than or equal to 1. 1/3, which is less than or equal to 1/2. So it looks like the terms are actually decreasing in this case. So my first criteria is met. Next, what about the limit? Well, the expression for Bn is this piece, this 1 over n. And so the limit of 1 over n as n goes to infinity is equal to 0. Both my criteria are met, therefore this series converges. What about the next one? Well, this one's a little bit trickier. What I'm going to do first is check the second condition. My expression for b sub n is this expression. And I want to look at the limit of that as I goes to infinity. In this case, because I have a quadratic in the numerator and a quadratic in the denominator, the limit as I goes to infinity is going to be the ratio of the leading coefficients. In this case, 2 over 1. So in this case, the limit as I goes to infinity of b sub I in this case is going to be equal to 2, not equal to 0, so I cannot say this thing converges. In fact, by the divergence theorem, I can actually say that it diverges. Okay, so now we can determine whether it converges or not, but if it does converge to what? Can we actually use this to approximate the sum of the series? So we saw in a previous video that if the terms are decreasing and the series is convergent, that if we add up the first n terms, we can use that as an approximation for the sum of the series. And then we can use the remaining terms, the r sub n's, as a representation for the error in our approximation. And the useful feature of an alternating series is that the magnitude of this remainder, of this error, is less than the magnitude of the next term. We represent that as the magnitude of r sub n is less than or equal to b sub n plus 1. So let's see what that actually means. Here we have that first series we looked at in the previous slide, and so once again we can write out those terms: 1 minus 1/2 plus 1/3 minus 1/4 plus dot 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 dot. And the idea is we could use the first two terms of this series, 1 minus 1/2, to approximate the total sum of the series. In this case, I would say the sum of the series is approximately 1/2. But that's not the exact value of the series, and so there's some sort of error. And what we're saying here is that the error is that r sub n. In this case, that error is less than or equal to the value of the next term. So that's going to be 1/3 in this case. So the sum of the series is approximately 1/2 plus or minus 1/3. And so that will be more and more accurate the farther we go out in the series. Let's explore the next one using Mathematica. So here I have a Mathematica notebook open, and I have the argument for this series typed in. Now if I use the table command, and I let those values of I go from 1 up to some other number, 10 for instance, this will generate the terms of that series. So I can see the first one be 1/5, the next one be negative 1/3, so on and so forth. And if I put a decimal in, I can see a decimal out. That might help me kind of view these a little bit easier. And so here I have my value of 0.2, and then the negative 0.3, 0.29, negative 0.23, so on and so forth. Now the first thing I notice is that my series doesn't look like it has decreasing terms. I went from 0.2 for my B1 value to 0.3 for my B2 value, and then to 0.29 and so on and so forth. However, it looks like that first case was really the only case, and I could explore that if I went a little farther out as well. And so while initially it looks like my criteria are not met, what I can argue is that if I look at all of the terms of my series past the first one and call that a new series, that series does meet the properties of my test, and that series would converge. And if I take that series, I simply add on one finite number, whatever that first term was, 0.2, that doesn't really change the convergence. So even though initially it doesn't look like it meets my criteria, eventually it does meet that criteria, and really we call that the tail of the series, or all the elements past some point, and as long as the tail behaves properly, then I can say that my series converges. So really, after that first term, the rest of my b's are decreasing. What about the limit? If I analyze this analytically, I can say because the numerator has a second-degree polynomial and the denominator has a third-degree polynomial, that the limit as I goes to infinity would be equal to 0. So in that sense, I've met both of my criteria. Now let's see if we can approximate a value for the sum of the series. And so what I really want to do is just add up maybe the first several terms. So let's say we add up the first 10 terms. So what I can do is just look at the first 10 terms, and then if I simply change my command from table to sum, this will add up the first 10 terms. So this is what I get when I add up the first 10 terms of my series. I get negative 0.020062. So in some sense that should be an approximation for the sum of the series. But it's not the exact value for the sum of the series. There is some error. Let's see if I can find an expression for that error. Well, the error should just be the next term here. So if I simply take this term here and I plug in I equals 11, that should be that next term. And so we can evaluate that and see what the error should look like in my approximation. The error looks like it should be 0.09. So I would say, what's the sum of the series? It's negative 0.02 plus or minus 0.09. And now actually in Mathematica, we can calculate the exact value of this sum just kind of to verify that we're going through our process correctly. So if I simply change this last piece to infinity, Mathematica is powerful enough to be able to calculate that exactly. And so this just helps me confirm my answer. So for instance, my approximation was this value, plus or minus this value. So if I take my approximation and I add in my error term, I should get a value that's bigger than the exact value. So I'll run that. I get 0.07, that is bigger than 0.02, so I have confirmed the value is correct. So in conclusion, if we have an alternating series where the terms in the series are non-increasing and the limit of those terms goes to 0, we can say that our series converges. And then we can approximate the sum by adding up the first n terms, and then the error in that approximation is simply the magnitude of that next term. Alright, that concludes this video on alternating series. Thank you.